Okay, so Bezier curves, what these are is it's a way of modelling parametric equations, and they do pop up occasionally, but it's a pretty rare sort of type of exam question. If you look at the curriculum statement, it's a way that it's a possible teaching, it's a way of conveying parametric equations, non-uniformly varying parametric equations. So it is in the textbook though, so we'll just sort of touch on it and explain it a bit. And we've got a couple of dot points for you there, just about what they're used for. So named after Pierre Bezier. I've heard it pronounced lots of different ways. I've heard Bezier, I've heard Bezier, I've heard I can't remember which one was said now, but so he was using them to model cars and to model the curves of cars. So we use it in CAD software and other 3D modelling. And an n degree Bezier curve is defined by using n plus 1 control points. So for our purpose here, we can see we've got 4 control points. Okay, so that's going to give us a degree of 3 Bezier curve. And that's the highest that we will look at. You will look at smaller degrees, but this is the highest that we will look at. And so we have the definition for a Bezier curve up here. We've got the x value and the y value. We restrict the t parameter between 0 and 1. So let's get straight into the example. We have these 4 control points, and we're trying to come up with what is the polynomial that describes the x coordinate with regards to t. Well, the first coefficient of the x cubed term is this here. All right, so all we're doing is we're taking all of the control points and evaluating this formula. So if this is our first point through to our last point, all right, then the subscript, x0 corresponds with this coordinate, x1 corresponds with this coordinate. So all we're doing, it's not overly challenging, it's just very methodical and even a little bit tedious, this process, which is probably why it's not so much examinable, because of the sort of methodical nature of it. It's very long and methodical, easy to make one simple slip up. So let's get in anyway. So x3, what's going to go here is the third x coordinate, so that's minus 4. Then we have to take away 3 times x2, which is 4, plus 3 times x1, which is 14, and then take away x0, which is 0. And so then we're just evaluating that and simplifying that. So what have we got here? 42, take 12 is 30, take 4 is 26. All right, so our first coefficient is 26. Okay, and then you just rinse and repeat for the second and third row, just following the formula there. So 3 times x2, so we'll have 3 times 4, take away 6 times 14, plus 3 times 0. So what will we have there? 42, 84, minus 84 plus 12 will be minus 72. Keep it just cracking on. 2, 0. Okay, so we've generated all of these coefficients, and I'll just point out at the top box we've got x of t equals a x t to the 3 plus bx t squared plus cx t plus dx. Okay, so we've solved through for a, b, c, and d. So we're just going to plug those into the x of t equation. We'll have 26 t to the 3, take 72 t squared plus 42t, and then plus 0. So we don't need to write that one. So this is the x coordinate along the Bezier curve. And then you would repeat the process for the y coordinate. So you would have the x coordinate and the y coordinate, and you go ahead and graph that. I won't repeat the process for the y coordinate, you're just following the same formula written alongside there. Does that seem okay? Yeah, cool. All right, so that's how they're generated. Let's get into an application of them though, like we've got in question 2. We've got a Bezier curve is defined by. So we have x of t is minus t squared, take 10t plus 2, and y of t is 2t to the 3 plus 3t take 5, and all Bezier curves are restricted for t being between 0 and 1. Alright, sketch using technology. So we covered this yesterday. We're in our graph mode. Just have a standard V window to begin with, and we can adjust it as we need to. Here's our x parameter, here's our y parameter, and we just need to make sure that we restrict t in our V window. Remember, t is right down the bottom, between 0 and 1. And remember, the pitch is like how many iterations are we calculating, how regularly are we calculating iterations. So we want that to be a small number, 0.05, 0.02, something like that, so that we have a nice curve. All right, so if we've sketched that, what mine looks like, restrict that to, anytime you reset your V window to standard, it will adjust the constraints. So I'm just going to provide a very rough sketch of it for now. This is what it looks like. Okay. Determine the domain and range of the Bezier curve. So the domain is the possible x values. So the possible x values go from here to here. Alright, so we need to figure out what's that leftmost point. So trace along, or you have your scale on there, we can figure it out in that manner. Alright, so I have when t is 1, the y value is, I've got all the rate of change values, I can't quite see it. 1, I have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. T is 1, this value here is x is minus 9. And then we've got when t is 0, the x value is positive 2. And that coordinate is minus 5, and that coordinate is 0. Okay, so now we can answer both of those effectively. So the domain will have minus 9 is less than or equal to the x value, which is less than or equal to 2. And the range, possible y values. Now the lowest y value is the point closest to the bottom of the graph. That's going to be minus 5. And the highest y value is 0. Hence, what is the highest, the lowest, the leftmost, and the rightmost point? This follows directly on from our domain and range. So the highest is y is 0, or we can list them as coordinates, I suppose. The lowest is x is 2, y is minus 5. The leftmost, minus 9, 0, and the rightmost is 2 minus 5. Now, it just so happens in this circumstance that our leftmost and our highest correspond. That won't always be the case. Like when you have curves that do something like this, okay, that would be, then they wouldn't match up, would they? They do in this circumstance, but that's merely coincidental. All right, so that's an application of Bezier curves. So let's crack in and have a go at the exercise. Seems okay.